video for Chapter 6, Human Population and its Impact. We're going to spend a lot of time today talking about human population dynamics. Something to remember, human population growth is considered to be the root of all environmental issues, regardless of whether we're talking about pollution, habitat loss, global warming, or energy resources. The number one thing that we can do to reduce the problem is to slow down the rate of human population growth. More people on Earth means more pressure on the natural systems. It's really that simple. So let's talk about human population dynamics. The beginning of your chapter talks about this core case study of China, and I find it interesting that it labels China's population growth slowdown as a success story. Yes, in fact, since the 1960s, China has done a lot to reduce its population growth. There was a serious threat of mass starvation of the Chinese people. So the government basically established these really extensive, intrusive, and strict family planning and birth control program. They promoted one-child families. They promoted contraceptive use. They promoted the sterilization of women. They promoted abortions of children after one child had been born in a family. But they also promoted these benefits, better housing, more food, free healthcare, salary bonuses for families that just stuck with one child, as well as they provided preferential job opportunities in the future for that one child. So basically what they were able to do is they were able to cut their birth rate in half over a span of 38 years. The average number of children per woman went from 5.7 to 1.5. But since 1980, they've been undergoing some rapid industrialization, some rapid economic growth, which is basically putting a major strain on their resources because they've got a rapidly growing middle class. And the ever increasing size of that middle class is actually increasing the middle class's ecological footprint. So really what we've got to address here is, why do we need to care about human population growth? Okay, we all depend upon the Earth systems to meet the basic needs for air, water, food, etc. And as the population grows and incomes rise, basically what that does is it increases the standard of living as incomes rise, and it will therefore increase ecological footprints. One of the interesting facts in this core case study that what I read at the beginning of the chapter was that currently we're not meeting the needs of 1.4 billion people on Earth, so 1 out of every 5. And what you need to ask yourself is, if we're failing to meet the needs of 1 of every 5 people right now, what are we going to do in 2050 when there are projected to be 2.7 billion more people than there are right now? So what we need to look at is, why has the population grown exponentially over the last 200 years? Okay, well, we've developed the ability to expand into almost all of the climate zones and habitats on Earth. We've had early and modern agriculture allowed us to grow more food for every unit of land area that we farmed, and death rates have dropped sharply because we've improved sanitation, we've improved healthcare, we've developed antibiotics, we've developed vaccines, which have helped to control infectious diseases. So really, when you think about it, the world population explosion during the last 100 years hasn't taken place because of a sharp rise in birth rates. It's actually taken place because of a sharp drop in death rates. So let's talk human population dynamics. The world population currently is almost 7 billion people. The rate of population growth is 1.1%. The 3 most populous countries in the world are the US, India, and China. You can see that the US is growing at almost 1%. India is still growing pretty rapidly at 1.5%, and China has, as we said before, has really slowed down its population growth rate. It's at 0.5%. So the total fertility rate, as you can see here, the number of live births on average that each woman of a nation will have during her life. The countries with the lowest total fertility rate will have the lowest population growth. More developed countries, really their replacement rate is about 2.1. Replacement rate is the number of children a couple need to have to replace themselves. So you're dealing with zero growth. Lesser developed countries, their replacement level fertility rates are much higher. And the reason for that is you have to take into account infant mortality rates. So in lesser developed countries, there's a higher infant mortality rate, so that replacement level will actually wind up going up. Um, total fertility rate is affected by a lot of cultural and economic conditions. Um, Cultures where women achieve a higher level of education tend to see much lower total fertility rates because women pursue career opportunities after they finish their education. Government policies, like we saw with China, affect total fertility rates, especially if there are regulations regarding birth control availability. So they can regulate that availability for birth control is virtually non-existent. So the total fertility rate would obviously go up there. And many cultures actually traditionally view a woman who has many children as being more prosperous or, quote unquote, a better wife. This type of tradition certainly has a great deal of power to drive up the total fertility rate. So let's talk fecundity versus fertility. Fertility of a population is overall can be determined by the number of women who gave birth in the previous year. So here's an example. If there are 2.5 million women out of 136.7 million women overall that gave birth in the year 2001, then the fertility rate would be calculated as such. So you divide the number of women who gave birth by the total, multiply by 100%, and right there is your fertility rate. The fecundity rate is actually determined by the number of women who have the potential to give birth in a year. So there you're actually looking at women of reproductive age. So let's extend the example that I just gave you. If there were 52.9 million women that were of reproductive age in 2001, then the fecundity rate would be calculated by 52.9 divided by 136.7. Create a percentage out of that, and that's 38.7%. So the natural annual rate of increase, it's calculated using the difference between the crude birth rate and the crude death rate for a population. Birth rate is the number of childbirths per 1,000 people in a year. Death rate, number of deaths per 1,000 people in a year. So here's an example. If a population has a birth rate of 12 per 1,000 and a death rate of 4 per 1,000, the natural annual percentage increase of its population would be 12 minus 4, which is 8 per 1,000. Adjust the decimal to reflect it as 0.8 per 100, or a 0.8% increase. Now, it's absolutely possible for this number to be negative. If you have more deaths than you have births, then obviously you're going to wind up with a negative number, so it's actually going to be dealing with a population decrease. The growth rate in the last century has really been affected by technological advances. The Industrial Revolution and the agricultural and medical advances that followed led to a population boom as lifespans increased and food supply was more stable. People in nations in the 21st century, people in nations with the greatest access to technology, are now choosing to have fewer children, resulting in decreasing rates of population growth. Let's take a look at doubling time. Doubling time is a statistic that's used in population dynamics, and it basically you're figuring out the number of years it's going to take for the population to grow to twice its current size. And to figure this out, we use the rule of 70. It's an equation that allows us to calculate by dividing 70 by the percentage population growth. So doubling time is equal to 70 divided by the percent population growth. Take a look at this box. It's almost guaranteed that there will be a growth rate calculation on the AP exam. As long as you're familiar with and you remember the rule of 70, you're going to be fine with this. So here's a slide that you're going to do some math practice on. This is going to be something that will be due in class on Thursday, January 29th. I'm going to put this slide in at the end of this presentation as well. All right, let's talk about social and environmental problems. Let's talk about world hunger. According to most estimates, there is enough food being produced on a global scale to feed all of Earth's population. So really what we need to think about is, why are people still dying of starvation and malnutrition? Well, the food supply is not distributed equally among all people. In more economically developed countries, or MDCs, people have far more food available than they need. In fact, much of it goes to waste. In less economically developed countries, there's often a severe shortage of staples like rice and grain. Poor management of croplands certainly leads to the loss of arable land as soil fertility is diminished. And in many LDCs, the population growth has outpaced the people's ability to provide food on a local scale. It's made even worse by the fact that extreme poverty is also very common. Now, let's talk about disease. As population growth leads to more people living closer together, which is increased population density, opportunities for outbreaks of disease dramatically increase. We talked about this last chapter, this being a density-dependent factor. Some diseases require a vector or a middleman that carries the infection from one organism to another. Vector-borne diseases cannot be passed directly from one person to another. Here's some examples. Malaria. It's caused by a blood-borne parasite called Plasmodium. It's transmitted by the female Anopheles mosquito feeding on the blood of an infected person, then passing on the parasite to the next person from whom they feed. The bubonic plague. It was transmitted from one person to another via fleas. And ticks. Ticks are common vectors for a variety of diseases, including bacterial infections, chemical toxins, parasites, and viruses. One notable bacterial disease is Lyme, which is transmitted through contact with ticks. There are some older diseases that were thought to be totally eradicated during the 20th century that are becoming more common due to population growth, becoming more common due to complacency about vaccination, and because of antibiotic resistance. Some examples are tuberculosis, which is a bacterial infection of the lungs. It can be spread through the air by tiny particles from the cough or sneeze of an infected person. Another form of TB is spread through contaminated milk. Pasteurization of milk kills the bacteria before it can cause the disease. Malaria is another example. It's caused by a vector-borne parasite. It's common in warm, wet tropical areas near the equator. And cholera. Cholera is a bacterial infection that commonly spreads through an unsanitary water supply. And we've also got some emerging pathogens, which include newly discovered parasites, bacteria, virus strains that are causing a host of quote-unquote new diseases. A couple of examples: HIV and AIDS. It was first discovered in the 1980s. Although it's not exactly new, HIV is still a recent pathogen in evolutionary terms, especially in sub-Saharan Africa. A person infected with HIV can be symptom-free for several years before becoming ill with acquired immune deficiency syndrome, which is AIDS. This makes the virus difficult to eradicate because people can be unaware that they're infected and can unknowingly spread the disease through sexual contact or the sharing of blood. Recently, we had H1N1, which was swine flu. It was first detected in the US in 2009. It quickly spread worldwide. The virus caused a great deal of worry, especially because of misinformation about how it was transmitted. A lot of people thought that eating pork was the cause, which in fact it wasn't. And then there's SARS, which is severe acute respiratory syndrome. It's caused by a coronavirus and spread through close personal contact, either by inhaling airborne droplets from a cough or sneeze of an infected person, or through touching a contaminated surface and introducing the virus into the body. In 2003, SARS was first documented in Asia, and it rapidly became a pandemic, affecting more than 8,000 people throughout North and South America, Europe, and Asia. So really what we're talking about here, the major issue here in the field of public health is human populations aren't geographically isolated anymore. Because of the increase in air travel, disease outbreaks that were formerly contained to just a small single group of people now have a much greater potential for reaching pandemic status. So let's talk about resource use and habitat destruction. Two major aspects of population growth make it an important factor in all other environmental problems. You've got the increasing world population and increasing per capita resource use. As there are more people on Earth, if per capita resource use stays constant, every additional person puts additional demand on our already limited resources. This is especially true of freshwater and arable or farmable land. In reality, per capita resource use is really not remaining stable. As more nations continue to reach higher levels of economic development, the people's standard of living is also increasing. So not only are more people being added to Earth's population, but each person is also consuming more and more resources with each passing generation, and this is a major, major problem. As you can see on this graph here, look at how resource use has exploded since the 1940s. I'm going to stop the video here. I'm going to create another one where we start talking about more developed versus less developed. So go ahead and watch both videos, but just to keep their length down, I'm going to go ahead and stop it here, and we'll pick up right at more developed versus less developed on the next one.